Okay, last one. So, we're going to prove something today. I have some real number alpha. I have integers, a0, a1, a2, and so on, which came from the continued fraction expansion of alpha. I claim if you want the numerator and denominators to the convergence, Pn and Qn, then the formula you're going to use is that your P0 and Q0 are just A0, 1. And then from there on out, to get the next numerator and denominator, your next numerator Pn is An times Pn minus 1, the previous numerator, plus your Pn minus 2, the previous numerator. And then your next denominator, Qn, is going to be An, taken from the integers up here, times your previous numerator, Qn minus 1, plus your previous denominator, Qn minus 2. So let's actually prove that. In order to prove this recursion formula, I'm going to need a proof by induction. So remember that every proof by induction has 3 steps you're always going to follow. Number 1 is the base case. You got to prove that your formula works from the very beginning. Number 2 is the induction hypothesis. We're going to state the thing that we assume, that it works, that our formula works up to some finite n. And then finally, in the induction step, we use the assumed formula to prove that the formula then works on the next step. So my base case here is P0 on Q0 equal to A0 on 1. So I have my continued fraction. A0 is the integer part. Then my first convergent is just the integer part, which is just A0 on 1. So yes, this bit about P0 is A0, Q0 is 1, that totally goes through. In my induction hypothesis, I'm going to assume that this formula for the recursion actually does work. So you can check this for n equals 1. Do I get an times a1 times p0, a1 times q0, and so on? Does that actually work? It does. So I'm going to assume this holds for some n, and I'm going to prove that the formula holding for the previous n means that it must be true for the next n as well. The induction hypothesis is always a pretty small step, but it's very important to state your assumptions in this kind of proof. So what am I trying to prove? I'm trying to prove that the next numerator is an plus 1 times the previous numerator plus the previous numerator, and likewise for the q's. Now, the fraction that I want with numerator Pn plus 1, denominator Qn plus 1, is the result of this finite continued fraction expansion, starting at a0, going up to an plus 1. I'm going to be a little sneaky and say that this is the same thing I would get if I took a shorter continued fraction expansion. a0, a1, a2 are all the same, and the final one of these is an plus 1 on an plus 1. Is that shorter? Well, the breadcrumbs are kind of obscuring it here. This list has n plus 2 things in it, right? 1, 2, 3, 4. an would be number n plus 1. an plus 1 would be number n plus 2. This list has only n plus 1 things in it. A0 is number 1, A1 is number 2, an plus this fraction is number n plus 1. So this is a shorter continued fraction. I'm being a little tricksy here because this term, this last bit, is not an integer. It's an integer plus some fraction. So when I put all of these numbers into the continued fraction formula, I'm allowed to use my induction hypothesis and say, well, this will be some numerator p n prime. This will be some denominator q n prime. And what are my formulas for this p n prime and my q n prime? It's the last a, which is my an plus 1 on an plus 1, times my previous denominator, which is pn minus 1, and my previous numerator, pn minus 2. These two numerators came from my a0, a1, an, so those are exactly the same, only I'm using a different an in my formula, in my recursion formula, so I get a different numerator pn prime. And likewise for the denominators, this will be an plus 1 on an plus 1 as my multiple. I've got qn minus 1, the previous denominator, plus qn minus 2, the previous denominator. So this should be a way to write the fraction that I want to solve for. Okay. Let me work this out a little bit. So here I've got the same information copied from the previous slide. I'm going to multiply through the parentheses and say this is an pn minus 1 and 1 on an plus 1 times pn minus 1, right? So I've just expanded that out on the numerator, expanded the same thing out on the denominator, and now I claim here I've got the number an, the previous numerator pn minus 1, the previous numerator pn minus 2. Well, what is that but my good old pn from my convergent approaching alpha. And I've also got this 1 on an plus 1 pn minus 1 hanging around. Looking on the denominator, the only difference is I'm using the letter q instead of the letter p, so the algebra still checks out and I get qn, my current denominator for a convergence to alpha, plus 1 on an plus 1 times qn minus 1. Okay, so what's that? This is the fraction I've got from the previous slide. The numerator and the denominator have a fraction built into them, right? That 1 on an plus 1. And whatever this fraction reduces to should get me the convergent that I want, my pn plus 1 and my qn plus 1. So I'm going to use one of the oldest tricks in the book. I have a fraction. I'm going to multiply the numerator and the denominator both by the same number. I'm always allowed to do that, as long as that number is not 0. So I'm going to multiply through by an plus 1 on the numerator and an plus 1 on the denominator. So here I'll get an plus 1 times pn, and then that will cancel the fraction 1 on an plus 1, and I'll get my pn minus 1. And similarly on the denominator, I will get an plus 1 times qn plus qn minus 1. So I get exactly what the recursion formula says I'm supposed to get. My next a times my current denominator plus my previous denominator. My next a times my current denominator plus my previous denominator gets me my next numerator and denominator. So I have proven this formula using induction. And again, this is mirrored in our PDF notes if you want to check and see a different exposition of this formula. But this means that we now have a way to calculate these things. Let's see how that impacts our approximation lemma from last chunk of this lecture. I said if I have some real number alpha, I have the nth convergent to alpha, then the difference between alpha and Pn on Qn is going to be less than or equal to this fraction. I said 1 on Qn times Qn plus 1. Well, Qn plus 1, I'm going to use my recursion formula and say this is the next A with my current Q and my previous Q. So I've just done a direct replacement here. And now I can simplify the formula and say, well, an upper bound for that has got to be an plus 1 times qn squared. I'm just going to multiply that through. And I should have a qn minus 1 times qn. But I'm just going to exclude that. I'm just going to drop it. So I've made my denominator smaller, which means I have potentially made my fraction bigger. So this fraction here is less than this fraction here. How good is my approximation to alpha? Well, it depends on your current denominator q and your next integer part, an plus 1. So no matter which convergent I'm looking at, it's going to be the same qn as over here. Yeah? But it'll be a relatively better approximation when I have a large value of n plus 1. So think about this. If I'm calculating continued fractions, I'm using my algorithm, I'm pulling out integer parts. When do I know to stop? When do I have an idea that the continued fraction I'm on will be a good approximation? I'll know that when the next an that I pull out is large. So in practical terms, going back to my example of pi, the reason why 22 on 7 is a good approximation to pi is because my next integer part that I would pull out is 15. And I know that because of my corollary now. I don't even need to calculate the next Pn plus 1 on Qn plus 1. I don't need to calculate this difference and figure out how many decimals it matches. The lemma just gives me a formula I can use every single time. So if you have stopped at Pn on Qn and you know what the next integer an plus 1 is going to be, without doing any more reciprocals or subtraction or decimal places or anything like that, this formula tells us how good the approximation is. All right, so that's been kind of a lot. If you need to, I encourage you to go back through the last couple minutes to make sure you follow along with the induction proof. And you can do that with any of these pieces of the lecture depending on if any of those parts are giving you grief. So make sure that you've got a good handhold on the continued fraction stuff before attempting the tutorial. I'll put a spot on the website where you can collaborate with other students as you're working through this stuff?